We know how vector-valued functions describe a particle's position, velocity, and acceleration. We can apply those functions to find the path of an object undergoing projectile motion. Projectile motion describes the trajectory of an object that is launched and then falls, influenced by only the force of gravity. More specifically, this video goes over ideal projectile motion, since we are ignoring air resistance and any additional forces. Since gravity is the only force present in ideal projectile motion, the only acceleration on the object is the acceleration due to gravity, which is constant. This is the equation describing the position of an object undergoing projectile motion. This is the vector written in ijk notation, and remember I hat, j hat, and k hat are the unit vectors in the x, y, and z positions respectively. Here it is in component form. R is the position vector as you know, v is the velocity vector, and v0 is the initial velocity or v of 0. G is the acceleration due to gravity. On Earth, this is approximately 9.81 meters per second squared, or 32.2 feet per second squared. T is the time, which is the independent variable, and alpha is the launch angle. This is the trajectory for projectile motion on an xy plane. Here's r of t changing for increasing t or time values. Here's the acceleration vector when the projectile is at different points during the motion. Notice how they all point down with the same magnitude. These acceleration vectors should be identical, since they are constant. During the particle's motion in the air, acceleration vector a equals 0, negative g. The velocity vectors are tangent to the curve and point in the instantaneous direction of motion. If we take a look at v0, this is when the projectile gets launched. Most of the time, the launch is at an angle above the horizontal. Alpha, the launch angle, is the angle between the horizontal and v0. Diagonal vectors can be broken down into their component vectors. In this case, v0 can be broken down into v0x and v0y. Throughout ideal projectile motion, there is no horizontal acceleration, so there is no change in the horizontal component of the velocity throughout the trajectory. The initial horizontal velocity would be the same throughout, so v0x can be written as just vx. Using trigonometry, we can find that vx equals the magnitude of v0 times the cosine of alpha, and v0y equals the magnitude of v0 times the sine of alpha. Going back to the velocity vectors along the curve, we know the length of the horizontal component of velocity is going to be the same as time increases. Since there is a constant downward acceleration, if the projectile was launched with v0y pointing up, the vertical component of the velocity vectors is going to decrease in length as time increases. Vy would then equal 0 at the maximum height, and then as the projectile is falling down, the vertical component of velocity vectors will point downward and increase in length. That is the equation of motion if the projectile was launched at the origin 0, 0. Now, let's say the projectile is launched at x0, y0 instead of 0, 0. The point where the projectile is launched is just shifted horizontally and or vertically, but the shape of the trajectory does not change. There's a vector x0, y0 that starts at the origin and terminates at the point where the projectile motion starts. So vector x0, y0 can be added to the base projectile motion equation to get the overall curve of the projectile position. Problems won't typically change the initial x position. x0 is usually 0, and we won't usually include it on the equation. But most problems do have an initial height, and y0 is often represented with h or h0. So this is the equation that's mostly used for ideal projectile motion. Let's do an example. A ball is launched from a platform with a height of 20 meters with an initial speed of 30 meters per second at an angle of 40 degrees above the horizontal. And we're going to use g equals 9.8 meters per second squared as the acceleration due to gravity. I'm going to draw a diagram with the information that's given. The first thing we want to find are the vectors RFT, VFT, and AFT. For RFT, the position vector, we're just going to use the equation for the ideal projectile motion. We're given the initial height, the initial speed, and the launch angle. So we can plug those values in. The velocity vector VFT is the first derivative of RFT. And remember, the units for position are in meters in this problem, and the units for velocity are meters per second. We already know that the ball's acceleration is constant throughout its trajectory. The acceleration is always downward, and its magnitude is g. The acceleration vector is 0, negative g, or 0, negative 9.8 meters per second squared. If we want, we could check this. If we take the derivative of VFT, we're going to get the same answer. Part B asks the time when the ball hits the ground. And we're going to reference our position vector RFT for this. We're going to look at the y component of RFT, and we're going to set that part equal to 0, because when the ball is on the ground, that is when its height is at 0. This is a quadratic equation, and after solving it, you'll get two answers. And we want to take the time that is later. In this case, we find that t equals a negative time and a positive time, and we want to take the positive time. In general, we want to take the time that is later, because that is the time the ball is on the ground at the end of its trajectory. Part C asks for the range, and the range is the horizontal distance traveled. To get that, we look at the x value of the position function at the time the ball hits the ground, and we just solve for that time in part B. So we can take that value and plug it into the x component of RFT. And this is going to equal approximately 110 meters. Next, we want to find the time and the point of the maximum height. The ball was launched upwards, so the initial vertical velocity was pointing up. Since there is a downward acceleration, as time goes on, that vertical velocity will get smaller and smaller, and at the ball's maximum height, the vertical velocity equals 0. And then after that, as the ball is falling, the vertical velocity will point downwards and get bigger and bigger. At the ball's maximum height, the vertical velocity Vy equals 0. And to solve for this, we look at the y component of the VFT function. We're going to set 19.284 minus 9.8t equal to 0. This is to find the time when the ball's vertical velocity is equal to 0, and thus this is when the ball is at its maximum height. So the time equals approximately 1.97 seconds, and to get that point, we're going to plug that time into our RFT position, and the point of the ball's maximum height should be about 45.2, 39.0 meters. And finally, part E asks, what is the speed at which the ball hits the ground? Remember, speed is the magnitude of velocity. We have the time when the ball hits the ground, so we can plug in that time into the velocity vector VFT, and then we take the magnitude of that velocity. The speed at which the ball hits the ground is approximately 35.9 meters per second. Let's do example 2. A cannon fires a bag from the top of a 20-meter high cliff to hit a target that is 40 meters horizontally away and 10 meters high. If the bag is launched 50 degrees above the horizontal, find the initial launch speed and the time the bag hits the target. So again, I'm going to leave some room to draw my diagram up here. And I'm going to write out the RFT equation first. This is the position function for ideal projectile motion. And now let's separate the functions for the x position and the y position. Now let's see if we could solve for the initial speed, the magnitude of v0, in any of these component functions. We do have the launch angle alpha, that is 50 degrees. The problem here is we don't have a time given. The two variables we have left are x and t. And in this problem, we aren't given a time. We don't know the position of the ball at a certain time, except for the initial position. The initial x value would be 0 at time t equals 0, and plugging 0 and 0 in won't help. We are given another x position though, and that is at the target, which is along the path of motion. The point the target is at is 40, 10, and we actually want to solve for the time the ball is there as well. With two unknowns in the equation for the x position, we can't solve for the initial speed here. Let's look at the equation for the y position. Again, we are trying to find the initial speed, and we have the launch angle. We also have the initial height and the acceleration due to gravity. Like before, we don't have a given time at a point, but what we do have is an xy pair. We know the xy coordinates of a point that is on the path, aside from the initial point. What we want to do is get x and y in the same equation as the magnitude of v0 and without t. So what we're going to do is we're going to isolate t in the x equation. So we get t equals x over the magnitude of v0 times the cosine of alpha. And we're going to plug that value in for the t's in the y equation. Now we have the equation with one unknown, that is the magnitude of v0, which is what we're trying to find. Now I'm going to simplify and rearrange some terms. These will cancel out, and the sine of alpha over the cosine of alpha would give the tangent of alpha. And then I'm going to square the terms in this parentheses and pull the x squared out. Now we want to isolate for the initial speed. And then by square rooting both sides of the equation, we have a plus or minus. Speed can't be negative, so we'll take the positive value. Now, after we plug in the values, we'll get that the initial speed is approximately 18.14 meters per second squared. Now that we have the initial speed, it's easy to find the time at which the bag hits the target. I'm choosing to use the x position equation to find time because it is linear and simpler to use than the y position equation. And because the equation is linear, there's going to be a unique x value for each time value. That is not the case for y because it is parabolic and you can have the same y value for different t values. We can plug in our values for the magnitude of v0, alpha, and the x position at which the target is hit, and we'll find that that time is approximately 3.43 seconds.